Number 50, letter A. Find the electric field at the center of the triangular configuration of charges in figure 18.54, given that QA is 2.5 nanocoulombs, QB is -8, QC is 1.5. All right. So here's our little picture. And what I've done is I've drawn a circle, all right, that connects all the vertices of the triangle, right, of the triangular figure that would have been created there between the charges, okay? I'm going to leave, though, the triangle out for now. So I'm going to assume that they're talking about this particular center, where it would essentially be the center of the circle, right, that connects all three vertices of the triangle. Okay. Now, if that's the case, what's important now, if this I assume to be the center, then in order to find the electric fields produced at this particular point, right, I have to know two things. I have to know the charge values of A, C, and B, which they gave us, right, in the problem. That's great. And I also have to know the distance, right, between A and the point of interest, C and the point of interest, and B and the point of interest. So what I realize is that's what we don't know, right? That's really the unknown part. So why don't we try to find that first? So what I'm going to do here is I'm going to draw a line from each of the charges to the central charge, okay? Oh, excuse me, to the central point. Now what we realize here, hold on one second, let's do that. Okay, great. Now what we realize here is that all of these lines that I have drawn actually represent the radius, right, of the circle, right? This is a radius because it's from center to the edge of the circle, right? And this is a radius and that's a radius. They're all different. They're all the same length, but they're different points, right? Different radii around the circle. So now what I'm going to do is I'm actually now going to draw in the triangle that connects the three charges to one another. Okay, hopefully this comes out all right. That looks pretty good. So now, take a look at this particular triangle that's created right here. Okay, what triangle is that? Or let me highlight it instead. This triangle right here. What type of a triangle would that be called? Equilateral, isosceles, or scalene? It's isosceles because two of the sides of that triangle are the same. How about this triangle that's created? Same thing. Isosceles, and then how about this? Isosceles, right? Now notice each of them all have these common R's, right? So if this side, so let's just pretend we're looking at this particular triangle right now. Well, not pretend, we're going to do it. So if I know that this side here and this side here are the same as one another, then I know this angle inside the triangle and this angle inside the triangle are also equivalent, right? It's like that opposite angle side thingamajig, right? Who remembers the name? I definitely don't. So what I realize then, that these angles I know will be the same, okay? You can call them X, you can call them theta, you can call them whatever you want, right? Just don't call me late for dinner. Okay. So what we're going to do is now we're going to look at this particular triangle, okay? And I also notice that they're the same R's, right? So these angles are all also the same as well. In the same triangle, that's an X and that's an X, right? But these are also the same as well because they're all related to the R value of the sides, right? All the sides are the same length. Same thing we would realize, and let me back out of this now a little bit. Same thing I would realize about this third triangle, right? All of these angles are equivalent to one another. Now remember, if you had X, 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 and X, you know that all the angles inside of that red triangle have to add up to 180. So you basically got 6x is equal to 180. So x is equal to what? 30, right? And you could have said, well, yeah, of course. I mean, look at this, right? I mean, I'm drawing a line to the center. I know this whole thing is 60, so half of that is 30. Yeah, that would have taken about 30 seconds. Well, actually 10 seconds, but I decided to take the more scenic route. All right, so we know that the angle in there is going to be 30, all right? So let's just choose this particular angle to work with, 30. Okay, now what I'm going to do is I'm going to create a new triangle. Who said geometry isn't interesting, right? So now I'm going to create this little half triangle. Now let me ask a particular, well, let me try to make that a little better. Let me see if there we go. Okay. So now, we know the angle in here. Do we know any of the sides of this triangle? This green one that I just drew? Well, we actually do. Now remember, the whole, as they said on the bottom here, each length of the triangle here in red is going to be 25 centimeters. So if this line goes directly down and splits the CB segment here in half, then I know that this little green piece is going to be 12.5 centimeters, right? And if I know this part of the right triangle, there's a right angle that's perpendicular, then can I find this particular R? Sure, right? Sure. We'll just do a little trig, okay? So this is going to be cosine of an angle, right, is equal to the adjacent side over the hypotenuse. So the cosine of 30 will equal that adjacent side of 12.5. Now, why don't we just convert that into, we know we're going to need it in meters eventually, so let's just do 0.125 all over then the hypotenuse value, which is just the R. So solve this bad boy for R, and what do we get? 0.125 divided by cosine of 30. So we get about 0.1443 meters. Okay, so that's the R value. Now, guess what? The nice part about this is that all of them are R, right? So hopefully that's cool. All right, now that's really what I need to do all this geometry for. So let's just get rid of all this now. And let's select that central point again. Okay, right here, let's just say roughly. Now let's talk about the vectors that I should draw at this particular point, the electric field lines. So we need to know the charges, right? So QA is positive, they told us in the problem. QB is going to be negative, and QC will be positive. So remember, from positive charges, the field lines point away, and therefore, at this particular point, I can draw a vector pointing directly down, and this vector pointing directly down will represent the electric field produced by charge A at that point. Great. Now, how about for B? Well, remember, B is now going to be negative, and all the field lines point toward a negative charge, and therefore, I'm going to draw a vector from that point pointing toward B, and therefore that I'll represent it as the electric field, produced by charge B. And now, last but not least, charge C. It's positive, so the lines emanate away. They point away from the charge, and therefore I'm going to have, some kind of a line over here that might look like this. Something along these lines. Okay? And we'll call that E sub C. Okay. Now what I should do is I should find the components, first, I guess I could find the magnitudes of each, right? So why don't we just find all these magnitudes, okay? So E sub A, right, the electric field produced by A at that point will be equal to K times Q sub A all over R sub A squared. So all I have to do here is just plug in now 8.99 times 10 to the 9th times Q sub A, they told us is 2.5 times 10 to the negative 9, right, coulombs. So this is 2.5 times 10 to the minus 9 coulombs. And I know it's negative, but remember it's the absolute value, so just leave it alone. And then the R, we just found the R, so let's plug that in, 0.1443 squared, okay? So E sub A here will be, let's do it, 8.99 times 10 to the 9th times 2.5 times 10 to the minus 9th divided by 0.1443. And here we get a value of about now 1079.4-ish, okay? And that's newtons per coulomb. Now that represents the vector over here, right, in the picture, E sub A. So why don't we create like a little mini, let's see. What I'm going to do here is just take this R value just so I have it. Let's just move it on up here for now. And why don't we move, what should we do? All right, let's move this down here a little bit. I'm going to erase this work, and let's create our component table, okay? So we have our vector. We have the X component, and then we have our Y component. Okay. And the first vector we did was E sub A. Now, what's the X component of E sub A? Well, it's pointing directly down, right? So we can see that in the picture, that's 0. And what's the Y component? It's going to be negative because it's pointing down 1079.4. Okay, great. Now, what I'm going to do is find the components now. Well, first I'm going to find E sub B. Okay, so instead of E sub A over here, I'm going to find E sub B. So the only thing that's going to change now is the Q value, right? Because the R value, the distance was all equal as we saw before. So this won't change. The only thing that's going to change for my calculations now is the number for B will be 8 times 10 to the minus 9th in here. So why don't we calculate that? Okay, so E sub B, so 8.99 times 10 to the 9th, times then 8 times 10 to the minus 9th, all divided by 0.1443 squared. And this comes out to about now, E sub B will be equal to 3,453.95. So I guess 3454 for now. Okay. And last but not least then, how are we going to do C? We're going to do C in the exact same way. So C now is going to be, instead of this number, we're going to plug in 1.5 times 10 to the minus 9th. Okay. For the charge. So 8.99 times 10 to the 9th times then 1.5 times 10 to the minus 9th divided by then 0.1443 squared. Oops. 443 squared. Well, I messed something up. 1 second. 8.99 times 10 to the 9th times 1.5 times 10 to the minus 9th divided by 0.1443. Oh, not again. You silly goose. Okay. So this is going to be now 647.6. So 647.6. And that's, again, these are all newtons per coulomb. I'm just going to leave out the units for now, okay? But those are all newtons per coulomb. So let's do this. So let's take all of our answers here, and let's just move them out of here for now. We'll move on up there, okay? Let's get rid of all this work. And now what I want to do is start writing in then the vector values, okay, the components, I should say, for now E sub B. So E sub B, okay? So what's the x component of E sub B? Oh man, it looks like we're going to have to do a little more geometry now, right? Yeah, I'm just going to breeze through this part. All right, so which means that the video will take, an extra half an hour, I guess. Because whenever I say that, for some reason, it seems like I take longer. I'm not sure. Basically, if I had to, consider this particular triangle, well, let me put that in blue. If I had to consider this particular triangle over here, right, and you knew this angle is going to be 30 degrees, if you notice, this angle should be the exact same, right? Because that's basically a similar triangle that's formed over there, right? It's a straight line. Well, that's not perfectly straight. But it's a straight line, right, that goes from this point all the way to that point. So if I draw another kind of horizontal there, just like this horizontal, then this angle in here should be the same as that angle in there. Okay? So what I realize now is that that angle up there is going to be 30 degrees. So this is 30. Okay? And what do you think then about this particular angle over here? What do you think? Do you think that's 32? I think so, right? You can draw it on out, right? You can draw your little triangle here and whatever, and then figure, this angle is the same as then that angle, and these are opposite then interior or opposite vertical angles. I don't even remember. Right? Who cares about the names? As long as we get the right answer. So we got those angles. So now how do we find? Now remember, if I know, let's look at E sub B here. If I know E sub B's value and I know this angle, I know to find the x component then here for E sub B will be a cosine calculation, because that's the adjacent side to the angle and this is the hypotenuse. If I want to find then the y component of that, I know I'm going to be using sine because I'm talking about the opposite side. All right, so this I'm just going to run through. I'm not going to write it out, right? So this is going to be, I'll talk it out. So this is 3,000, let me get the exact value. Okay, 3,453 multiplied then by cosine of 30. That's going to give me the x component. And that x component is approximately, yes, 2,991. Okay, so where shall I write that in? So for E sub B, that's the x, and it's positive, right? It's going to the right-hand side, so that's 2,991.2. And then how about the y component of that? So now we need to do the sine, okay? So let's now do the sine. So we got that exact number. 1 second. So, what are you doing? What are you doing? So let's take the sine now of 30. And it's pointing, though, in the negative direction, right, in the picture. So that's going to be a negative value in here. So that's going to be here negative 1,726.97. So I guess 117.27 is 1,727. Perfect. Then E sub C now. Okay, E sub C. Okay, let's extend these lines on down a little bit. And we have a positive x component for e sub c, so let's take its value, 647.6 roughly. I'll try to, oh no, I graphed something. Oh God. I hate this calculator because whenever you graph it, you can't quit it until I get like 4 graphs. Sorry guys. Sorry for this little intermission. You know how, like on the calculator, you can't then, you know, hit and clear, but the graph just got a graph. You can't stop it, right? Okay, so we're going to take that 646, multiply it by cosine of 30 to find the x component. So it's 560.9-ish. So that's 560.9. And then the y component, which is positive. So we're going to take now the sine of 30. And this is 323.8. So this is 323.8. All right. Now, guys, let's just add it all together. Okay. This, once we add these together, remember, we get then the resultant vector. So we're going to get the resultant vector of the electric field, the components of it, okay? So take your 2,991 and then add it to that 560, excuse me. And I'm doing exact values, so in case the math exactly on the screen doesn't work out precisely to how you think it might, it's just because I'm using the exact values. We're only going to be off by a decimal. So in the grand scheme of it, honestly, who cares? So we got that. Then we're going to take the other values and add them together. So we got the positive 323 minus then the 1727. So let's get that. And then minus the other value of 1071. Where is that one? That one's all the way back. Oh, no, excuse me, 79. There we go. Okay. And this is going to be negative 2,482.5. Okay. Problem's pretty much over now, right? All we have to do now is just basically find the resultant vector. So we can just, you know, draw this resultant quickly. We have an x component in the positive x direction of 3,500, about 3,500. Then we have something in the y direction, right? Negative. So we're going to have it a little smaller. Negative 2,000, you know, 2,500-ish. I'm just drawing this to plot it out. And then we have the resultant vector here that I just drew in. This is the final value that we have to find. So how do we do that? Remember, we can just use that resultant formula, okay? So it's the square root then of the sum of the x's times the, square root of the sum of the x's squared plus the square of the y, sum of the y's, okay? So this is 3,552.1 squared plus negative 2,482.5 squared. All right, and these are both squared like that, so let's find it now. So the resultant vector here is going to be square root of that thing squared plus this thing squared. And we get a value of about 4,333, right? Or aka 4.33, I guess that's fine. You know, how many sig figs? My mind is numb at this point, so honestly, who cares? So this is going to be 3, and this is in newtons per coulomb. Okay? All right, great. And there we go. All right. So now we got the resultant electric field. What we can do now is, if we wanted to, we could also calculate the angle, right? In here, if you wanted. So that's just going to be a tan calculation of the y over the x there. So take the inverse tan. So basically, it's just going to be inverse tan of the y component, which is 2,400. Well, let me do the exact values, right? So we'll do the inverse tangent of the 2,482.5 divided then by the x component of 3,552. Calculate that, and we get about 34.9 degrees. So that theta in there, so theta is going to be about 34.9. Okay, degrees. And then that's going to be, we can call it south of east. If you want to state it from the positive x-axis in the positive direction, by all means, knock yourself out. So, yeah, that's letter A, guys. And now guess what we get to do? Letter B. All right, let's do it. Letter B. What do we have here? Is there any combination of charges other than this that will produce a zero strength electric field? No. Guys, thanks for tuning in. Please remember to help us out and subscribe. We appreciate it very much. Thank you for tuning in, and we will see you next time. Take care.